welcome back. Thank you for coming for part 2 of this tutorial on pseudorandomness and meta-complexity. Let me take you back to where we stopped last time. So I discussed this 2 ways to use the generator, play to win and play to lose. So just to remind you, you have some kind of generator construction based on some secret message or secret string, truth table function f in this case. And the generator has some nice reconstruction properties such that if you break the generator, you can recover the secret message f. So it's kind of, you can think about this as kind of distributional encoding of a message. So you take a message and rather than outputting a single string, you output a distribution on strings with the property that if the distribution is not, it can be distinguished from the uniform distribution, then you can recover the message back. Okay, so it's kind of a different kind of error-correcting encoding, decoding paradigm. And you can play the game to win so that the generator is not broken. And usually that happens by choosing the output parameter to be somewhat smaller than the intrinsic complexity of the message that you start with. And you may choose to play to lose, so you want to use the reconstruction property to recover the message. So you need your generator to be broken, and usually you achieve this by choosing your output length a bit too large compared to the intrinsic complexity of the message f. And like intuitively, if you use little randomness and you stretch it out, information theoretically does not contain enough randomness in it. So if you can tell whether the output of the generator has enough or not enough complexity, then you'll be able to break the generator who's overstretched. Okay? And so we'll see examples of these 2 approaches in application to meta-complexity. And usually the algorithm that will help us to get a distinguisher, will help us to break such a generator, will be some kind of heuristic to estimate the complexity measure of the string. So in the example of Randomness, that would be a heuristic that would be able to tell you how hard a truth table is with respect to circuit complexity. And it's enough, you don't need to compute the circuit complexity exactly, but something that Rasbarov and Rudich called natural property would suffice, and we'll have similar assumptions on average case easiness of time-bounded Kolmogorov complexity in a second. So let me remind you, natural property, intuitively, it's an algorithm, efficient polynomial time algorithm, that has the following properties. On all the small complexity strings, it accepts. And for at least half of all possible random strings, it rejects. Okay, so it allows you to tell easy from random in this precise sense. Okay, so it's much weaker than just computing the complexity exactly, but just telling easy from random is sufficient. Okay, any questions so far? All right. And now for something completely different. So I'll be talking about meta-complexity, and we'll show you how pseudorandomness is a useful tool to get some interesting results, some connections for meta-complexity problems. What are meta-complexity problems? Well, one of them is a minimum circuit size problem. Given a string and the size parameter, tell me if the string, viewed as a truth table of Boolean function, is computable by a circuit of small size at most s. And the other one is Kolmogorov complexity version of that, time-bounded Kolmogorov complexity version of that, MKTP, sometimes denoted as min-KT. Given a string and 2 parameters, the size and the time, is there a description of length at most s such that some universal Turing machine fixed in advance, U on the description D outputs the message X within T steps. Okay, Igor defined those things yesterday, but just in case, this is the repeat. And since these questions involve complexity themselves, the area which studies the complexity of the questions about complexity has been termed meta-complexity. Okay, and these are kind of 2 natural examples.
T is given in unary, I guess.
Usually, yeah.
Okay.
Usually S and T are both given in unary, yes. And we'll see that when actually going to be using that notion. Thank you. Any other questions? So basic open question is, what's the complexity classes which capture these problems like MCSP or MKTP? Both are easily shown to be in the class NP because you can always guess a program and then run a universal machine for T steps. And if T is given in unary, then it's going to be polynomial time verification procedure. So the problem is in NP. They seem to be like hard enough to maybe be NP complete, but it's still open whether they are. Another question is, well, are they easy to compute? Maybe they're in polynomial time, or maybe they're in polynomial time on average. And it turns out that they're probably not easy on average, because if you believe in crypto, if you believe that one-way functions exist, then you cannot have problems like MCSP or MKTP easy on average in the sense of natural proofs even. Because if you had such an algorithm, average case heuristic for MKTP or MCSP, you would be able to invert any candidate one-way function efficiently. So these problems, MCSP, MKTP, have lots of interesting connections to cryptography, learning, complexity theory, average worst case, and so forth. And so the randomness that we talked about in tutorial yesterday is an important tool for metacomplexity, and I'll give you some taste of how the pseudorandomness is used to prove some results. So here's my possibly ambitious plan for today. I'll talk about a certain generator different from NW, a generator based on Ehrkarting codes, Hadamard codes. Then I'm going to be using the properties of this generator to derive, under some assumptions, symmetry of information for KT, for K-poly. And then I'll hopefully give you some application to complexity theory, basically extending what Igor told you about yesterday, that result that he mentioned that average case easiness implies worst case easiness for NP. I'll provide more details of that. He didn't give you the proof, but I'll use symmetry of information to provide the missing steps of the argument that he outlined. If you don't remember what he talked about, don't worry, I'll repeat whatever is needed. Any questions so far? Okay. So Hadamard code DP generator will be used in the sense similarly to NW generator that I just reminded you about. We'll use it to distributionally encode messages with the property that if the distribution produced by the generator on a given message can be distinguished from the uniform distribution, then you can recover the message quite efficiently. And that would allow us to bound the Kolmogorov complexity, time-bounded Kolmogorov complexity of the message in terms of the parameters of the generator. And the Hadamard code direct product generator is chosen because it has very good parameters. Okay, so NW could be used, but you wouldn't get as good results as using this. So theorems would not be tight. So let's start with a definition of Hadamard code. This is a simple multilinear encoding of a message, and bit string x is mapped to a long, exponentially long string where you encode x by taking inner product mod 2 of x with all possible n-bit binary strings. And so you have inner product of x with all zeros, inner product of x with the next string, and so forth. So n bits mapped to 2 n bits. So it's very inefficient as far as codes go, but has very nice properties. The famous result due to Goldreich and Levin gave an efficient algorithm for decoding Hadamard code under a very adversarial scenario where you have corrupted almost half of the bits in the code word. And still, if you have a little bit more than half plus epsilon fraction of uncorrupted bits, in the code word, which of course you don't know where they are, you'll be able to recover the original message X with some precision. You'll get it as a one message in the list of possible candidates. Yeah, please stop me at any point if there are any questions. I hope to give you some details, but I don't have that much stuff to talk about, so I will dwell on some things because they're a little bit more complicated than the simple stuff that I talked about yesterday. I'm not going to prove this a result of Goldreich-Levin, so let's just read what it says. Basically, it says that you can decode. More precisely, there's an efficient polynomial time randomized algorithm. Sometimes I'll be sweeping randomness under the rug because we'll have access to pseudorandom generators, as you shall see in my assumptions, so we can always de-randomize whenever we need to. So randomized or not, or deterministic will not be a big difference under our assumptions. So there's an efficient algorithm A that, given access to its algorithm or circuit, which maps n bits to 1, such that the circuit agrees with the encoding of a message X on more than half of the positions. So C of R agrees with inner product of X and R for at least half plus epsilon of R's. Okay, so you know more than half of the bits of the correct encoding of a message. And if you have that corrupted code word, but with some non-trivial agreement with the actual valid code word of the message X that you had in mind, then the algorithm can recover with probability 1/2 a list of not too many strings, like 1 over epsilon square. So advantage epsilon becomes bound on the list size, which contains the message X in question. And in a very precise way, this is kind of the best you can hope for because you don't have enough information to recover the X exactly. You only have like half plus epsilon agreement. If you had like 3/4 agreement, then yes, possibly, you could do that. But half plus epsilon, like 51% agreement, is not enough. So you have a bunch of possible X's that will have the agreement with the same C. Okay. Any questions about this result? Which I'm not going to prove, but we're going to be using as a black box, in black box fashion, to define and analyze the direct product generator based on these Hadamard codes. I'll pause just in case so you can.
So you're saying that there's more than one X that has disagreement? Or
Yeah.
are you saying that by querying few positions?
So if you give me C that has agreement with X encoding of X in more than half of the positions, that C could have the same agreement with an X prime as well. Okay.
X and X prime are different
Yes.
position, then we can get something in the middle which agrees with 3/4 with this and 3/4 with that. So you cannot avoid this list decoding.
Right, right. Yeah, so you just don't have enough information about the corrupted code word. The amount of corruption is a bit too much to have unique decoding. So as Sasha was saying, this is the regime of list decoding, when the corruptions are so many that you cannot recover the original message exactly, but you can have a bunch of candidates such that your message in question, X, will be among those candidates. And then, of course, like jumping ahead a little bit, once you have this collection of not too many possibilities, then you can identify which X is yours by telling me the index on the list of the X. And that will be like additional information that will tell me to specify, to recover the X exactly.
Yeah, so is n squared divided by what? It's not clear. Epsilon?
Epsilon to the 4th.
Ah, to the 4th.
Yeah, it's not going to be important for us. It's like, yeah, if you want to be really super careful. Okay. So the generator that we'll define using this Hadamard codes will be basically kind of direct product application of Hadamard codes. So you take your message X, think of X as n-bit string, and you look at X in a product Z1, x inner product z2, x inner product zk, where you have some polynomial number of z's that were chosen as part of the input. So you basically output positions and the values in those positions of the Hadamard code. Not just one position, but like k of them. Okay? And you know which positions.
What means DP?
Direct product. Yeah, so it should be called like Hadamard direct product, but it's been called direct product by Shuichi Hirahara, so that's what I'm using. And you see it's kind of direct product. You have a bunch of z's, and you do the same thing independently a bunch of times. And the result that makes this generator useful is the reconstruction property of this generator with good parameters, as I was alluding to before. So the result due to Hirahara is the following. Assume the randomization assumption that exponential time contains functions of exponential circuit complexity, which we know is equivalent to having a good generator with exponential stretch that folds linear size circuits. Then there's a polynomial p such that if some time t uniform algorithm d is a distinguisher for this generator, so it distinguishes its outputs from the uniform distribution, then you can recover the hidden message x, and the time to recover x will be this polynomial in t, so polynomial in the runtime of a distinguisher, which makes sense. You need to run the distinguisher. And how much you need to specify to recover x? Well, exactly k, where k is this how many strings z's you pick, okay? Plus some small amount, like log n amount. Okay? So I'll let you stare at this and yes.
It's not a real generator because the length of output is equal to the length of input.
No, it's bigger. If k is big enough, so k can be polynomially in length of x, polynomially big in length of x. So then it gives you a little bit of stretch. It's important that it produces more bits than the input size, so you can actually hope to break it by making it overstretch itself, and then it outputs something which does not have much complexity. So using our assumption that we'll do next, that you can in some way estimate Kolmogorov complexity of strings, time-bounded Kolmogorov complexity of strings, you'll be able to break this generator, and then you'll have your distinguisher D that you can plug in here, and you will upper bound the complexity, Kolmogorov complexity of a string x. You encode it using this generator by this parameter k. And then you'll be carefully choosing this k. Okay.
So
Yes.
there is the generator which we should distinguish. Doesn't depend on the function which exists in E and requires large circuits. Just some fixed generator.
This circuit complexity assumption gives you the pseudorandom generator that you'll use to get deterministic Kolmogorov complexity here. If you don't have that, then you'll get something similar for probabilistic Kolmogorov complexity, time-bounded, the notion that Igor talked about yesterday. And actually, I'm going to point you exactly the place where PK complexity was born. It's in the proof of this lemma that I'm going to show you. Okay? So without this derandomization assumption, you cannot derandomize, so you have to use randomness, and then your reconstruction of X will be randomized in the probabilistic complexity way sense PK that Igor talked about yesterday. But if you have this derandomization assumption, then you can get everything deterministic, so deterministic Kolmogorov complexity will be this.
Valentin, but it seems that even if k is smaller than n, x is fixed.
Yes, X is fixed.
That means that your seed has length nk. Your seed is z, right?
My input is the whole thing.
But it's
Sorry. My X is fixed. My X is going to be fixed, yes. And then my seed is length nk. My output is nk plus k.
Plus k, so k bits more.
Yeah, k bits more. Yeah. Yes, as I wrote up here. Yeah. Yeah, so
you have written there that it's k minus n bits more, but actually it's k bits.
yeah, yeah. It's, I hope it's clear. Right, so yeah, you have, if you ignore the x part, then you have a little bit of stretch, but not something to write home about. But we're not trying to use generators to de-randomize algorithms now, but we try to use them to encode things distributionally, and then use our assumptions to break the distribution, distinguish it from uniform, and then decode to recover the original message.
But still in the assumption, the distinguisher should distinguish this distribution for a fixed x?
For a fixed x.
For a fixed x.
Yes, for a fixed x.
So what is the exact model? So x is fixed.
X is given to you in advance. For this fixed x, you define the generator, which outputs this stuff. For random z's, it produces this outputs, which is the same z's plus extra stuff, which gives you some information about the fixed message x. And then you try to distinguish this distribution from the uniform distribution. And if you can, you'll be able to get your x back. Yes?
So I don't understand. So k is supposed to be maybe bigger than n.
K is going to be bigger than n, yes.
But then the upper bound on the Kolmogorov complexity is trivial. No? So is that k really? Or?
No, so it's Kolmogorov complexity upper bound on x.
So it's interesting when k is less than n.
Yeah, sorry,
Right.
sorry. Yes. It's not, yes. K here will be Kolmogorov complexity of x, basically. Yeah, so it will be less than the length of x. Yes.
Yeah, I guess the confusion is, okay, k is less than n, the length of x, but when x is fixed, you still have some stretch in the generator.
Of course.
Yeah, I guess that's what
Yeah.
Yes.
For example, we can think of k as n over 2.
For example. Yes. For example. Yeah. So let me prove to you this lemma. It's not hard, and I hope to give you fairly complete proof. So we argue by contradiction, or rather, we assume that you have a distinguisher D that distinguishes the distribution output by the direct product generator from the uniform distribution of appropriate parameters. I'm not sure if I have the, I think they're right here. So output of generator is of length nk plus k, and the uniform distribution is on strings of length nk plus k. So I have hybrid argument that I'm going to be using here, and I'm going to go from the output of the generator distribution at the top to the completely uniform random distribution at the bottom, and I will gradually go from the top to the bottom by fixing or by changing rightmost bits one at a time to random bits. The usual hybrid argument that we saw. So you can tell apart the top distribution from the bottom distribution by the assumption that D is a distinguisher, which means that there must be some place, without loss of generality, I'll say the beginning part, so that you can tell apart the top distribution from the next distribution. Okay, in general, it can be in some arbitrary place, but without loss of generality, let's focus on this. So if your distance between the top and the bottom was like 1/3, and you have k intermediate distributions in this picture, then there will be two successive ones, two neighboring distributions that can be distinguished by this distinguisher D with distinguishing probability like 1/3 over k, or 1 over 3k. Okay? So by Yao, you get a predictor with a correctness probability half plus advantage, like 1 over 3k. And in this picture, since I have a distinguisher that works for the top distribution and the next one, I'll be able to compute x comma zk, because I can tell it from the random bit. So Yao allows me to predict this thing with probability something like half plus 1 over 3k. And this is going to be my epsilon that I'm going to be using in the Goldreich-Levin algorithm in a moment, but we're not done yet. But eventually, once I have this predictor, with some caveats that I will talk about in a second, I will use this predictor as an input to the Goldreich-Levin's algorithm to recover the list that will be of size 1 over epsilon square, which will be like about k square, that will contain my x. And then for that additional cost of like log n, I will identify my x on the list by telling you the index on that list. And that will give me the reconstruction of x with these parameters that I claim. Okay? So that's at a high level what's to come. So all I said, everything I said kind of almost works, except for some annoying issues that you need to deal with these preceding bits. When you fix things, you need to like do something about this randomness z1 through zk, and also these evaluations of x inner product z1, z2, and so forth, zk minus 1. So before, yesterday, we were very generous, and we just said, it's advice, hardwired non-uniformly, pick it by averaging, done. Now we want to be very careful about the amount of advice that we actually have to give. And if something we can not use as advice, we don't want to do it. Okay. So in particular, the randomness, z1 through zk, is completely uniform randomness. So think about randomized reconstruction algorithm. So it will flip randomness z1 through zk, and then with high probability over chosen randomness for z's, it will get this prediction probability for x dot zk. Okay, so randomness z1 through zk will not be fixed. It will be random. But with still this annoying issue of having these inner products, x z1, x z2. So that will be our advice. And the amount of advice will be, in the worst case, k. And that's the k that is stated in the lemma. That's where it's coming from. Okay, this advice. Note that the advice, these bits, inner products of x with z's, is dependent on the randomness in z's. So it's not advice which is fixed in advance, but you flip randomness, and based on the randomness, the advice comes out something. So that is exactly the definition of PKT, where you flip randomness first, and then you come up with a description based on the randomness. This is exactly where it's coming from.
But you have not PK.
I know. But we have randomization assumption that will help us to get rid of randomness. It's coming. But if you didn't have randomization assumption, you would have to use this notion PKT here. And that's where it comes from. Okay? So the result that Igor talked about yesterday follows similar argument, but because we don't have the randomization assumption, you have to use randomized reconstruction, and the notion of Kolmogorov complexity that is natural is not randomized KT like RKT, but it's actually PKT because of this stuff here. Hopefully this is clear. So this is where PKT is born. Okay?
Why do you need to log PT, that term, the second term? In the statement.
In the statement. Yeah. Yeah, you need to decode. So it's maybe it's smaller than this, but just to be safe, it's some logarithmic term, log n term. Yeah. I don't remember if you really need large polynomial there, or maybe just log n is enough, but definitely it's a valid upper bound. Okay, but because we don't want to use PKT notion, we want to use KT notion, we have to do something about the situation at hand, that we have randomness chosen first, and then we have advice dependent on randomness. So how do we deal with this? The solution is to use the Nissan-Wigderson PRG that maps log n random bits into polynomial many, in this case, n times k pseudorandom bits. So think about this distinguisher D. What do we know about D? D is efficient uniform algorithm. In particular, it's a small circuit. Yes? We know that this small circuit distinguishes this distribution from the uniform distribution. If you replace the z's to be the outputs of a pseudorandom generator G on log n bit seeds, D will not notice the difference, because generator G fools all small circuits, including this guy D. So we can get rid of the z's and compress them into logarithmically shorter seeds, and D will still do its distinguishing job as before. Its running time will increase because now it has to run G, the Nissan-Wigderson generator G. Okay, and that's one of the things that will come into this running time polynomial T in the Kolmogorov reconstruction later. So it takes into account the running time of the generator, Nissan-Wigderson generator G. Okay, so
sorry, I don't quite follow because the advice depends on the randomness.
So I'm not done yet. So just give me a second. So I'm just saying that the distinguisher D does not need to use completely independent random Zs. So what we'll do, we'll fix not the Zs, but we'll fix the seed sigma that will determine the Zs as a mapping of this Nissan-Wigderson generator G of sigma. So before, we were trying to fix the Zs, and they were too big as advice. But now, instead, we're going to be fixing sigma, which is only logarithmically small, as advice, and we can afford that. Once we fix sigma, which will determine the Zs, the advice bits x, inner product Z1, and so forth, are also fixed. And now we add them to the advice as an extra k bits. And so we'll have, with this advice of k plus something logarithmic, a predictor which can be used as an input to the Goldrake-Levin decoding algorithm. And then Goldrake-Levin will run this predictor we got and get a list of something like k-square candidates containing x. So at an extra additional cost of like log k, which is like log n, bits of advice, I can exactly specify x on that list, and then I'll recover x. So we conclude that the time to recover x using this distinguisher is going to be some polynomial, which includes the runtime of the Nissan-Wigderson generator, Goldrake-Levin's reconstruction algorithm, and Yao's predictor. And the bits of advice that you need to recover x is going to be basically k plus some small logarithmic term.
And T is what?
T is the running time of the distinguisher D. So you start with assumption that some distinguisher D running in time t can break this direct product generator. And obviously you need to use D somehow, so its runtime t will be the parameter of the final reconstruction time. Any more questions?
So what about the randomness of Goldrake-Levin?
Yeah, I'm sweeping this under the rug, but it can be dealt with in a similar way by using Nissan-Wigderson generator. So like everything can be derandomized. I just showed you the most important piece where derandomization is happening. Other places where it's happening can be handled even easier than that. Okay, so basically whenever you need to use randomness, you use NW generator and use the small seed and add that small seed to the advice, and it will be small enough so that the main term will be k plus the rest will be something logarithmically small.
Am I wrong in saying that actually the Nissan-Wigderson generator is used on Z1 to Zk minus 1?
Yes.
Not to Z1 Zk because they're frequent.
Yeah. Well, I'm gonna ignore some things.
Oh,
Yeah, it's for notational.
That was correct from my.
Correct. You are correct. Yes. So whatever, depending on where the hybrid argument happens, it will be those Zs.
Yeah.
But you can always output more and then use less.
For sure.
Yes. Any questions about this lemma? Sasha?
No, the entire setting is quite new, so I try to get some general picture of it.
So it might be helpful to see how this is used. But basically, it allows you to get upper bounds on time-bounded Kolmogorov complexity of strings x that you want to get upper bounds for.
I'm sorry.
Yes, please.
I don't see where you're going to use the DK here. Maybe I missed something
I'm in this statement.
I thought you were gonna,
No, because of this assumption that you made in the first sentence here, I do not need to use randomized anything.
yeah, I missed something that I thought you were saying, this is what I'm going to read.
Yeah, so if I didn't have this randomization assumption, I would have a situation here. And that's where I would have to invent, which we did, probabilistic Kolmogorov complexity. In the definition, which is a bit funky definition, with like randomness first and advice later, which is actually was defined in an old paper by Travis and Vadan for similar reasons, and they had like advice with double slash instead of a single slash. So usually in complexity we have single slash advice, which means that advice is fixed in advance. Double slash means exactly that you pick randomness and then the advice depends on randomness. So it's the same thing. So it's PKT in disguise.
So just say it again, there is a length of x, which is, and k. So
Yes.
what is bigger?
K will be hopefully close to the true complexity of x. So K will be something less than length of x. So we'll choose K in applications to be the true Kolmogorov complexity of x, time-bounded, maybe still a little bit less than that, so that we can break or not break the generator. You see an application of this.
So x is a kind of a linear function, scalar product with x.
Yes, yes.
So we have some fixed linear function,
Well, you have a fixed x.
which just means that we fix x.
Yeah, just
X
think
is
about,
just a linear function on these
yes,
here. And then we look at values of this function at k places,
Yeah.
random places.
random places, yes, correct.
Then, if this place is random, they are probably linearly independent.
Probably.
So it seems that each new value will be just independent with the previous one. So
Yes,
Sasha, if x is random, but x is fixed.
yeah,
no,
That's
x is
important.
fixed, but still it's a linear function now.
Okay.
So if you take a random z1, so
so you're saying information theoretically, you have enough information to recover x. That's what you're saying, right? If you choose k large enough, like about the complexity of x itself, then k bits of information is enough information for you to know x. Yes? And this allows you to do that efficiently.
So we know this function of at some random points, and
Yes.
also we know that it's somehow simple. And from that we want to get it.
No, we know this function of some number of points, and we know that this distribution on those random locations and the values in those locations is not uniform, can be distinguished from uniform. And from that, you can describe x.
Sasha,
Distribution for fixed x.
For fixed x.
Sasha, think as follows. Assume that x is just a random linear function. Okay, fix a random linear function.
Yeah.
If you know its value in n points, then you know that.
Yeah.
But if you know its value in n over 2 points,
Yeah.
those values are completely independent.
Mm-hmm.
In the sense that you can't distinguish those values from truly random
Mhm.
values. That's important.
Yeah, exactly. So if you choose k to be smaller than the true Kolmogorov complexity of x, you don't get enough information, and actually you'll get uniform distribution indistinguishable from uniform. So yes, exactly. So you can choose, again, you'll have freedom to choose k the way you want. If you choose k to be slightly smaller than the true Kolmogorov complexity of x, the generator cannot be broken. If you choose it more, it will be broken, and then you'll get an algorithm to recover x. And this will give you an upper bound on Kolmogorov complexity of x.
But this will be broken apart. I mean, that will depend.
It will be broken by an assumed natural property style algorithm for computing KT. Because the output of this generator will analyze the KT complexity of the output of the direct product generator, which is basically the KT complexity of X itself. So if you know X and you know the Z's, you can compute the output of the generator. So the output of the generator dpk xz is essentially the complexity of X plus the descriptions of Z's, which is coming up. Is it okay to move on, Sasha?
Yeah.
Okay, so the application of this result will be a proof of symmetry of information for KT under assumptions. And so it was done around the same time independently by Hirahara and myself with a student, Haley Goldberg. So again, let's make this assumption, the randomization assumption, that E requires exponential size circuits, which as we know is equivalent to having PRG, which will help us to keep everything deterministic rather than randomized or PKT complexity. If you don't want to make this assumption, then you can replace KT with PKT everywhere and it works. But I want to show you the deterministic case here. Okay, so we need to make this assumption that will help us to break the direct product generator, and the assumption will be that minimum KT problem is easy on average, kind of natural proof style, and I'll tell you exactly what I want from this efficient algorithm for KT in the proof. Okay, so basically it will help me to distinguish easy strings from random strings, where easy will have small KT complexity and random are random.
This would already break one-way function?
Yes, yes, exactly. So, yes, you're jumping a little bit ahead, but yes. So let me read the statement. So you have generalization assumption. You assume kind of easy on average solution for KTP. So you have an average case, polynomial time, heuristic, errorless for solving KT. Then there is some polynomial Q such that for all strings xy and all large T, you have the symmetry of information down here. Kolmogorov complexity of xy is lower bounded by Kolmogorov complexity of x plus conditional Kolmogorov complexity of y given x minus some negligible log term. There are many experts in this room on classical information theory and Kolmogorov complexity. So statement like this is known unconditionally for time unbounded Kolmogorov complexity. And it's one of the classical results in Kolmogorov complexity. Here, as Bruno indicated, we cannot hope to prove a statement like this unconditionally because that would break cryptography, that would break one-way functions.
Does it go the other way around, the implication also? Is that known?
I think Igor will talk about this after me. So good question. Did he pay you? No. Okay, so that's coming up next talk. Stay for next talk. Yeah, so the argument, this is an argument why if you have symmetry of information, you can break cryptography. It's very simple, so might as well talk about this. So suppose you have candidate one-way function, which is a polynomial time computable function from n bits to n bits. If you have symmetry of information for KT, you can say that the Kolmogorov complexity of pre-image x given the image f of x is going to be at most the Kolmogorov complexity of a pair xy minus the Kolmogorov complexity of f of x. Okay, this first inequality is the most important step. This is by assumed symmetry of information. Now, for the next line, you just say, well, I know how to compute y from x, so I don't need both. I just need enough. It's enough for me to have x. So you can upper bound ktxy by k some bigger time x. And for the second term, well, if I know x, I will be able to compute f of x because f is efficient. Okay, so I can get rid of f of x and replace it by x, maybe with some bigger bound here. And now this thing looks familiar. This looks like computational depth. So Kolmogorov complexity of x minus Kolmogorov complexity of x, unfortunately with different bounds. Okay, but for most x, they're super hard. So their Kolmogorov complexities will be almost the same with high probability. So this difference will be most of the time something like log n, which means that most of the time, for most x's, you can recover x given f of x by trying all log n bit strings and doing everything polynomially. So in polynomial time, you break one-way functions. Make sense? Okay. So I want to prove to you this symmetry of information result. So it's not actually difficult. As one of my colleagues say, the proof writes itself. You just need to know the right starting point, and then everything else just follows almost immediately. So let's go through this. For any k prime, this will be the parameters of direct product generator that we'll fix later. But whatever they ought to be fixed, you know the following simple upper bound, that if you look at the output of the generator, so x and y are fixed like in the theorem, statement of the theorem, so they're fixed strings, x and y. And then you look at the generator, direct product of x given random z's, and direct product of y given different random z's. And k for the first and k prime for the second will be chosen in some way. But whatever they are, to define this whole string, it's sufficient for me to know x and y and to know z and z prime. And this is exactly what this inequality tells you. Okay, so this is easy, hopefully. Questions about that? Okay, so we're off to a good start. Now I'm going to use my assumption that MKTP is easy on average. Exactly what I mean is this, that for all easy strings, my algorithm will say yes, and for at least half of random strings, it will say no. So these are 2 bullet points here. Okay? So I assume this magical polynomial time algorithm B, which has these 2 properties. It can distinguish easy from random in this sense. Are you with me? Now the first magic step happens. We'll define k and k prime. We're not going to specify each one individually, but we'll fix their sum. We'll make the sum k plus k prime equal to the Kolmogorov complexity of xy plus some largish term. Intuitively, we want to make the DP generator output too much stuff so that we can, we can break it. Okay, so we'll make the output of my DP generator larger than the intrinsic complexity of the hidden messages x and y together. Okay. We'll choose the parameter s, which will be, okay, so where is s coming from? It's here. Okay, so remember we had this bound just a minute ago, the trivial upper bound on the Kolmogorov complexity of the outputs of the generator. Call this upper bound s. So we know that everything produced by the generator has Kolmogorov complexity at most s. We'll make k plus k prime bigger than that s. Okay, so k plus k prime will be such that the length of the output of the generator will be bigger than s, which means that generator is outputting more stuff than it should, right? It's overstretched. And from this it follows, there's a simple proof, that my magic algorithm B, average case heuristic for KT, is going to be a distinguisher for this direct product generator composed with a direct product generator for x and y, for the k prime such that their sum, which controls the length of the output, is too large for the generator's own good. Okay? The proof of this claim that we have a distinguisher is very simple. Here it is. We already know that S is upper bound on the Kolmogorov complexity of the output. So B on input, which is the output of the generator, will always say yes, because the outputs are always easy. So on outputs of the generator, we say yes. On the random strings, well, we have more random strings than possible strings of description size S. So by simple counting argument, at least half of the random strings will escape and B will say no on them. Okay? I'm not going to go through the simple calculations, they're trivial. Okay? So you have too many random strings, small s, things happen. Are we good with the claim? So what we have so far, we have ability to distinguish the outputs of the generator from the uniform distribution. Now we're going to play the hybrid game. So let me jump to the end, which is very close. So we now have the situation where we have outputs of the generator at the bottom here and the uniform distribution such that our B is a distinguisher between the top and the bottom. Now we're going to walk through the top to the bottom by changing U to dpk and keeping the other U the same. Okay. What we're going to show is that the top two distributions by the same B will be indistinguishable. Okay, believe me for a moment that that's the case. How are we going to use that? Well, if B can tell apart the top from the bottom but cannot tell apart the top two, it must be the case that B can tell apart the bottom two. Yes? And why is it good? Well, if he can tell apart these two, then by Yao, you can predict, or you can, not by Yao, but by reconstruction property, if you break, basically, you have two components of the generator. The first component is the same in these two distributions, so we can ignore it for a second. The second component tells you that you can distinguish dpk prime of y from uniform. By the reconstruction lemma that we saw, that means that the Kolmogorov complexity of y is going to be small. It will be at most k prime plus something. Okay, so now you need to remember that you have this other generator, dpk, which needs to be given to the distinguisher in some form, but all the distinguisher needs to know is this x. So what you'll get is conditional Kolmogorov complexity of y given x is going to be at most k prime, which matches the statement that we were trying to prove. The Kolmogorov complexity of y given x is going to be upper bounded by something. Okay, so this will be the proof of our symmetry of information result for a properly chosen k prime. Now, okay, so let me go back to this. So this will finish the proof. If I show to you that these two distributions are distinguishable, that will give me an upper bound on the conditional Kolmogorov complexity of y given x as k prime plus something. And then magically, k prime will happen to be exactly the quantity I want it. That's the sense in which the theorem proof writes itself. Okay? Remember, k plus k prime is fixed. I'm going to fix k in a moment, which will fix k prime. Magically, k prime will be fixed to exactly what I want it to be to get the symmetry of information result. So I only need to choose k. How do I want to choose k? I want to choose k so that these top two distributions are not distinguishable by b. Okay, so I want to play to win. I want to make sure that this generator dpkx is indistinguishable from u. How do I do that?
The output has to be
Exactly. The output of my generator, so parameter k, better be smaller than the true Kolmogorov complexity of x by some amount, by some additive amount. And this is exactly what I'm going to do. So I'll define k to be kpt complexity of x minus some small amount, so that this generator dpkx is indistinguishable from the uniform distribution. I'm running a little bit out of time, so I'm not going to tell you exactly how you choose the parameters, but as I said, once you have the idea, everything else is just simple calculation, which magically works out the right way. You just want to play to win here, which determines the value of k. Then you have k plus k prime fixed to something, and k is fixed to this. You work out what k prime is going to be, and it will be exactly what you wanted it to be. So you get this conclusion. So yeah, just remember what k plus k prime was specified up here. Okay, so k plus k prime is this quantity. K would be something like kpt of x. So k prime will be ktxy minus kpt of x, which is exactly what you want an upper bound on the conditional Kolmogorov complexity to be. Does that make sense? Have I lost everybody?
Maybe you can comment. So
Yes.
there is the classical for unbounded complexity. So we have this x and y. And this we split the complexity of xy into k plus k prime.
Mm-hmm.
And we need to show that either x has complexity at most k, or the conditional complexity of y given x is at most k prime.
Mm-hmm.
And then for non-bounded case, the splitting happens like this. We look how many for given x, how many other y have complexity together with x smaller than k prime.
Mm.
And here you also somehow split this into cases.
Yes.
But maybe you can repeat what is the criterion of splitting.
Yes, 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 yes.
Maybe this
Sure.
will
Yeah, so
maybe some-
the whole proof is summarized here,
yeah.
okay, in this picture. So you define the generator GPK, which encodes both x and y independently with different parameters k and k prime. And then you set the parameters k plus k prime so that this generator is broken, is distinguished from the uniform. And the way to do that is to make sure that k plus k prime is like bigger than the actual complexity of x comma y. So that's
You
your,
say somehow that either the first two are distinguishable,
Yeah.
or the second.
yes. I want the second two to be distinguishable.
No, but if the first are distinguishable, then x is simple.
Exactly. And I don't want that to happen. That's why I make sure that x is not simple by choosing the parameter k to be smaller than the complexity of x.
Okay, you can also say that you provide either it's smaller than
Sure, sure. Yes.
I want to say either the first is distinguishable or the second one
Yes.
is distinguishable conditionally.
Correct. Correct. Yes. Yes. Yeah, you have these two distributions so that like you can play, like in the first case, the uniform is easy, so there's no, like it's just randomness, so there's no dependence here. So you say if you break the first two, that would mean ignoring this part completely, the right-hand side completely. You have distinguisher between u and GPK, which allows you to get an upper bound of Kolmogorov complexity of x to be k. You choose x, you choose k to be such that this is not possible. Okay, so these guys are indistinguishable, which means that these bottom two guys are distinguishable, and then you look at the second component that the action happens, and the first, just the condition on x. So you have a conditional Kolmogorov complexity of recovering y given x to be at most k prime. And then the parameters just work out the way you want them. Does that make sense? That's pretty much a complete proof, okay? I may have swept something on the Dirac, like randomness, reconstruction, randomness, but we have the randomization assumption that can help us handle everything at the expense of extra log n bits of advice, which is negligible for us. Okay, so that's whole proof. And as I mentioned before, I repeat it again, if you don't assume the randomization assumption, but only assume that KT is easy on average, then you get the symmetry of information for PKT. Essentially the same proof.
And if MKTP is just polynomial everywhere, then you get something better.
Oh, I don't know. I don't know how to get anything better, actually. Like in terms of, like this is the symmetry of information you want, right? I'm not sure what would mean to be better than this statement. It may be that you get some other stuff, but in terms of the statement, I think that's the best you can hope for, right? And this up to the polynomials. How much time do I have?
You have 2 seconds, 1 second. That's an hour, but I suppose you can make the comment.
Okay, so I'm pretty much close to the end. I wanted to show you like more details of the stuff that Igor talked about yesterday. So he told you about this nice result of Hirahara that says that if sigma 2 is easy on average, then NP can be done in deterministic time to the n over log n. Okay, actually it's p to the NP because you can find the lex first witness in that time. So it's not NP is slightly better, but doesn't matter right now, it's pretty late. So if I can take like a couple of minutes, I'll tell you pretty much the sketch of the argument that you do. So at the high level, what you start off is under the assumption that sigma 2 is easy on average. You'll argue that the Kolmogorov complexity of, so you fix some NP verifier R. So you fix some NP language, which comes with the verifier R, X is an input, Y is a witness, and R is polynomial time computable predicate, the usual. Pick Yx to be the lex first, R witness. Let's assume it exists, so X is in the language, so it exists. Then you can use this average case as easiness assumption to argue that the total Kolmogorov complexity of X and Yx is upper bounded by X alone. And intuitively, this is because you can do search to decision. Okay, and this average case easiness assumption allows you to also then argue that you have reconstruction and upper bound the deterministic Kolmogorov complexity using this DP reconstruction lemma that I talked about, that I'm not going to show. The only step that I want to show you is application of symmetry of information in the argument, which is step number 2. So it turns out that if you assume that NP is easy on average, then you get both assumptions that I was using so far, namely that E requires large circuits, exponential large circuits, and KTP is easy on average. Okay, the second one is kind of trivial because KTP is an NP. Okay, so distributional NP being easy means that this problem is also easy. And the first implication is not, it's more difficult. It was proved some time ago using non-relativizing techniques, interestingly. But yeah, anyway, so you can unify these two assumptions with a single assumption like so. Okay, the point is that under the assumptions we make for this theorem to work, we have the assumptions that you need for symmetry of information to work. Okay, then apply the symmetry of information and argue that the conditional Kolmogorov complexity of the witness Y sub X given X is going to be some quantity which after some simplification becomes computational depth of X. Okay, KT minus K polynomial TX. Okay, so that's already pretty good. Means that on average for random X, you can recover the witnesses efficiently in polynomial time. If you want to do it worst case, there's a simple averaging argument that Igor kind of mentioned that tells you that if you choose your T to be large enough, then you can like argue that there will be KT complexity of Yx given X will be something like n over log n, where T is roughly to the n over log n. Okay, this is like a simple hybrid style argument. You partition the interval a bunch of times, and you argue that there will be two successive points which are close to each other. Okay, nothing very deep going on there. And once you have this bound, then you can recover the witnesses by doing brute force. And that's how you get the result. Okay, so that was probably too fast, but this was the second time you saw this result, maybe with some missing details. Does that make sense? So the only thing that I wanted to point out is this use of symmetry of information in this result. Any questions? I'm gonna, yeah.
Can you show the slide of this Hirahara theorem?
This one?
No.
The reconstruction one?
Yeah, about complexity.
The DP one? This one?
This one.
Yes.
So, as I understood, you used assumption about average case simplicity of MK
TP. Yeah, yes.
To get that direction,
To get the distinguisher here, yes.
If the complexity is small, then we have a distinguisher, right?
So if you have a way to solve KT problem on average, then for some settings of parameters of dpk, for some setting carefully chosen k, you can break this generator, which means that you'll get a distinguisher that allows you to get the upper bound on the Kolmogorov complexity.
No, the other way around. Assume that the complexity is large.
The complexity of what is large? Of x?
No, sorry. I meant the other direction. Assume that the complexity of x is small, right?
Uh-huh.
And then we want to prove that there is a distinguisher, right? And
Yeah.
And this, in this direction, you need average case
Correct.
complexity.
Correct.
So actually, for your symmetry of information, you need a weaker assumption that this theorem holds in the other direction, right?
I'm not sure I'm following what the other direction means. For symmetry of information, I'm using this result. Okay. So this result, let me step back. Remember NW generator? NW generator came with the reconstruction property, which says that if you break me, you pay so much, and then you recover the message. This is an analog of that. Okay, you have a generator construction which comes with a reconstruction property saying, if you break me, if you have a distinguisher for me, for that price, you get to recover X. That's all. Now, as with NW generator, I can play to win or play to lose by choosing the parameters properly. In the proof of symmetry of information, I use this lemma in two ways. Once I played to win, so that generator is not broken, and the other play I played to lose, the generator is broken. When I play to lose, I use my distinguisher, which comes from the average case algorithm for KTP.
Right.
Yes. Okay, so let me jump to the conclusion slide. Yeah. Yeah, so basically, hopefully you got a taste from these two tutorials on what pseudorandomness is and what it's useful for. It's useful for randomization, play to win, for learning, play to lose and do reconstruction, for analyzing properties of KT complexity that we just saw, symmetry of information, applications to complexity like average case versus worst case that I just briefly sketched for you, and probably more stuff that can be done. Okay, that's all I have to say. Thank you so much for your attention.